we go again. Let's write some more Wasm in PureScript. Hoping everything's fine. It's telling that I'm dropping a bunch of frames, so maybe I should just check that it actually worked on Twitch. So I can hear myself. All right, yeah, that's good enough. I've picked a new color scheme today. Maybe something that's not too low on contrast, but still a dark-ish thing. So no low contrast. No low contrast theme. And we can see if that works out. So, where did we stop the last time around? We were implementing signed LEB 128, if I recall correctly. And we're having some troubles with it because it's trickier than unsigned LEB 128. And I'm kind of close to just copying an implementation rather than trying to write it ourselves. And come back to this later because it's well, I'm not sure if this really does much for us here, or if we're not better off getting deeper into the Wasm stuff rather than just bit shifty, just a bit nonsense. But how about with this? We time box it for 15 minutes. So if we can produce a working implementation, it seems like I'm still dropping frames like crazy. Anyway, we'll try. If we can produce a working implementation in 15 minutes, I'm happy. If we can't, I'm gonna use a binding to an existing library. Just gotta let my cat in. All right, let's do this. So, let's go back to Wikipedia. So, encoding assigned. And that's decoding. Encoding assigned integer. Let's try to think of this one. Look at this one more. One more time. This is pseudocode. We could use the JavaScript implementation, I guess, and see if we can't just port that maybe, or try to understand what it's doing. So, well, it's doing this thing first, which that's basically making sure this is a 32-bit number. So let's try to do that. So we're going to say that Rx is actually, and I'm not sure, it might actually just, it might complain about this being, about this variable shadowing it. So I'm going to do this, and I'm going to say this is the same as bits.war 0. We need to put this in a fixed position. And so what are we doing then? The result buffer, yeah, we're just writing, we're writing to a buffer, so we don't need any result arrays. So this is a while true. Okay, so this is a while loop. And what does it do? Well, step one, it masks out the last 7 bits, which is exactly what we're doing here. And then it checks. And now this check is more complicated than what we did before, because here we just checked if the value was 0. Right. Well, yeah, okay, so it shifts the thing by 7. That's what we're doing here. So that's the shifted. And that checks if the value, and which is now shifted, is equal to 0, and this is where things get a little interesting, and byte, which is the 7 bits, bits dot ended with 0x40. So this is checking if the sign bid is 0. So if the shifted value is 0, we need to make sure that the whole thing was a positive int. Hey Vlad, how's it going? Nice to have you here. So we need to check that if that's the case, that this was a positive value to begin with because the sign bit then has to be 0. And if the value is equal to -1 here, so this is if that's in binary, that's the value represented as 1, 2, 3, 1, 2, 3, 4. So this is -1, which means that we're done. Make sure you get the boot, just leave them exhaust. Oh, I bet. Getting a baby to relax is probably one of the most unrelaxing things you could do. All right, so this is the value -1 in 2's complement. And so what we're going to do here is we're going to say if this happens to be the value, then we need to check that the sign bit is well, unequal to 0. So this means that this was a negative number. And if so, we are going to add an int and then we're done. So we're going to add the byte and not set the bit that tells it to continue. And PureScript that's a / equal. Also fighting with a pretty legacy Haskell project, getting it to work. Recent GHC and HLS, not fun. Yeah, I bet. I've not tried to get the HLS to work on anything, and because I try to do that on Windows, that's probably not a good idea anyway. I'm just gonna wait for 5 more years before they're ready for it. Well, with Nix, maybe you can get it to work if you've already bought into Nix for everything. That's been my experience with the more recent Haskell stuff. So any of the GHC.js or any of the Haskell language server, really the only way of getting these to run was to use Nix. Maybe I should try again these days. But yeah, GHC also changes quite a lot. So bumping the GHC version in is trickier than I would have expected when I first got into Haskell. I mean, I'm like 1.5 years into Nix and still spend a ton of time debugging stuff. Yeah, I mean, I use Nix at work and I'm not the hugest fan, but I also think for certain things there's no better solution than Nix right now. We don't have one, unfortunately, but I'm not convinced at all that Nix, just adding Nix to something makes it the thing better, basically. That's what I'm not convinced at all. Okay. So I'm going to try to push a little forward. So if this is the case, we're going to push the byte, which is this, and then we're done. If it is not the case, we are going to order the thing with 80. So we're going to set the continue bit. And then we are going to keep going, which is this while loop, which is actually just calling signed lep 128 on the shifted value again. Wait, no, it's not. It's, yes, it pushes it and then it does the while loop again, which starts out by doing these things. Yes. So maybe we can move. Well, I mean, we end up ORing the thing with 0 over and over, which is kind of inefficient. So I'm just not going to do that. I'm not going to bother. I'm assuming that PureScript is going to make sure, the type system is going to make sure that this is actually an int, which is a 32-bit integer value. I think it's really hard to create one that isn't in PureScript unless you're doing something silly. So I'm just going to leave it as is for now. So hopefully this is signed LAB 128, and we can try by making the program that we had yesterday, which if we can look at it here, it spits out a const 16. This is what we managed to generate yesterday, basically. And it spits out a const 16 here, and I wanted that to be a 10. But that's because I'm just writing the byte 10, but that's not actually what you'd how you're supposed to write that. So what we're going to do here is we're going to say signed LEB128 into the buffer, and we want to set the number 10. And also, I'm just an idiot because that's actually not 10. This is 10 in hex. So maybe I should have just, maybe we were fine all along. Yeah, we probably were. This is has actually been number 16. Anyway, I want to try and make this user signed LEB, putting in the value 10, which is actually 0x 0a. Since we're using hex just about anywhere else, I'm going to try to do the same here. No, actually, you know what? This is just so it matches const 10 up here. Okay, so let's try that one. I think we might need to change our main function to, yeah, do the actual encoding again. So let's try this one. See what we get. Okay, that looks fine. Let's also here, after every time we compile and run this file, use wasm to wat on the resulting bytes.wasm file. So, okay, that looks better. That looks like the thing we kind of expected. Now, supposedly, implementation we did also handles negative numbers, which I think we should try out next. So here I'm saying putting the value 10 on the stack. Let's try putting the value minus 16 on the stack here. I think we might need to wrap this up for this to work out. Okay. Going again, minus 16. Let's try a big one. Let's try minus 16,420, 500, I don't know, whatever. That one. That's more than a byte. So let's see what we can get here. So 16452 looks correct. So I'm gonna call this a win. I'm not sure if PureScript is able to recognize that this is tail recursion though, so maybe we actually need to do this for this to work out. It probably actually won't even spot it here. Whatever, should be fine. I'm also going to do that here. Right. Still looks correct. Okay, cool. So we've, I think we have all of the things we need. So this is write U32. How is that implemented? Oh, that uses this one, but we probably shouldn't be using that one. Let's just make sure. So in the Wasm binary spec, let's look at conventions and find the vector encoding one more time. And U32, a U32 is an unsigned LEB128. Okay, so we shouldn't be using write U32 because this one always uses the maximum amount of space for that number. So where we're using we're using it in these places. So this is just a copy of the thing above, I believe. So we're just going to delete that, and instead we're going to say, or wait, we're going to say this is actually just, so this is a U32, which is an unsigned number, and this is just unsigned LEB128. And then hopefully this still works. We should end up with a smaller result. Does it tell us the size of the file? Not really, no. and I'm going to get rid of these things. And we can inline this again, like so. Microphone's annoying a little bit. Okay. All right. So the message thing. Let's not do that. And now we need to fix a bunch of errors, which is fine. This one. This one. No longer need the console. That all sounds great to me. Let's clear out some of the comments here. All right, and then we're going to eventually figure out like a little interface for this so that we don't have to pass the buffer around everywhere, and we're going to use a type class to represent this in what I believe is called a finally tagless style or something, but we're going to build as ourselves a little DSL. Basically, that's the idea here. And we're going to remove these hard-coded things, because what we're doing right now, so I think this is good, because we can now move on to the part that is more, what I'd say, interesting, because so far we've just, well, handwritten some binary format here really, but this binary format that we've been writing so far really is a binary encoding for an abstract syntax, right? And that's that's actually what a module is in the Wasm sense, is represented as its abstract syntax. And so far we've been figuring out how to binary encode that abstract syntax, but now we need to actually define the abstract. So we've been writing a binary format for a specific AST, or a specific abstract syntax, and now we are going to start defining that abstract syntax and then encoding the whole set of the abstract syntax rather than just a single instance of it. So again, I would like, as we've done before here, I want to, this is not an encoder for the full format, and again, I also don't want to define the full abstract syntax for WebAssembly, because while it's reasonably small, it's actually very small for a intermediate representation, but it's still largish. So I'd like us to start by just defining the things we need to write our little test programs, and then making sure the pipeline works, and then we can always add more Wasm functionality into our library later. So what do we need to do? We need to create a new module. I'm going to call this syntax. So this is the module Wasm syntax, right? And this is the abstract syntax. Okay, so this defines let's actually use these like so. So this thing defines the abstract syntax of WebAssembly as a PureScript module. Well, not really. It's not as a PureScript data type, or as PureScript data types. Let's do that. Okay, so the first thing we see is that there's a module, and a module is a and we can follow the specification pretty much. A module has a bunch of components, and now again, I'm going to only add the components we care about, and one thing we'll need to figure out is whether or not we want to new type this module. I'll default to not new typing anything until we start needing instances for it. So for now, we're just going to deal with record types here. Okay, so types is a vector, which is, well, we're just going to use arrays for these, of func types. Okay, and that's not defined yet, but we'll just keep going for now. Or maybe we shouldn't. Maybe let's go depth first. Okay, so how do we define a func type? So we need a func type. So let's say we need a func type. And let's figure out how these are defined. And maybe we can backtrack from there. So function types classify the signature of functions, mapping a vector of parameters to a vector of results. They are also used to classify the inputs and outputs of instructions. And so a func type is a collection of result types. So, or like, is two result types. And we could consider making this a record as well. And say, well, for a func type, we have the arguments, which is, and the results. And both of these are result types, which is kind of a weird name, but we're going to stick with it anyway. So these are result types. And really what result types are in Wasm are arrays of value types. And so what does this mean? This means that the WebAssembly functions can accept multiple arguments, but they can also return multiple values. Because WebAssembly is a stack machine, we can put more than one value, like we can leave more than one value on the stack as our function returns. Okay, and so a result type really here is just an array of value types. Okay, and so what's a value type? Or how the specs calls them, val type. Let's try that. Let's try sticking with that. And I've capitalized all the types, all the trailing types here. So I'm going to do that there as well. And so now we finally get into the fun bit, so, or like the end of the rabbit hole. So value types are actually a subtype, where we have I32, I64, F32, and F64. All right, and so now we're going to backtrack. We're going to go back, and we're back in modules. Okay, so types, we needed that because we've written that out as a section. The second component here are funcs. And what is funcs? Funcs is an array, again, of func. Okay. So what is a func? A func is the function component of a module defines a vector of functions with the following structure. So a func has a type, it has a vector of locals, and a body, which is an expression. Okay, so we can order these later. I'm just going to keep adding them here for now. So a func is a record with three components. It has a type, which is a type IDX, so type index, and a type index is just an int. It has a local. It has a field called locals, and that's a vector of value types. So we're just going to use arrays here again of val type. And then the last field here is the body, which is an expression, and that's probably the most tricky type of them all, but we'll see. So the body is an expression, and expressions are defined down here as a sequence of instructions terminated by an end marker. I'm going to claim that we do not need to put that end marker in there in our data module, in our data types. Maybe that's wrong, maybe that's right, I don't know. I'm going to just go with not putting it in for now, because what does end even mean? End is a control instruction. Where's end defined? We'll see. I'm just going to leave it out for now, and we can figure out if that's a good idea or not later. Okay, so now we need to, an expression is a list of instructions, really, then. So or an array of instructions. And spec shortens that one, but I'm not going to shorten that because I think that's not a good idea. So WebAssembly has all of these instructions, and they are all basically, this is one large sum type. We could split it up into sums, which might be a good idea. I think ideally this would actually be a variant. But I'm going to define it as a, well, the variant would make it really easy to combine these. But I'm going to define them as a sum type for now, and then we can figure this out anyway. Okay. So instruction is a sum type. And let's just do, the I32, the simple binary operations or something. Let's just do those first. So we've got const, which const takes an inn, which is an integer or something. Oh no, I is the sign. Occasionally it is convenient to group operators together according to the following grammar shorthands. Natural disaster is following. Thanks for the follow. I hope you're having a fantastic day. We're trying to figure out how to define the Wasm instruction set as a PureScript data type right now. And I'm wondering if we should follow the separation the specification lays out here, or if we should just make this a large sum type for now and just add the stuff we need. I think we're just going to add the stuff we need for now. So we definitely need I32 const, for example. Right, but what we could do is we could say, well, we're going to make an I32 insters type or something, or I32 instructions, and have that have all of the I32 ones. But I think I'm just going to go with one large sum for now because that's easier to work with. And then, yeah, we'll see if that's a good idea or not. So an I32 const actually contains an actual number here. So this is it carries an int because, well, yeah, that's basically just how the I32 const thing is defined. And then we have all of the union operations, and because that's so few, I'm just going to write these out. So we're just going to do I32 for now, and then we might do all of the others later. So CLZ, I don't even know what that is. I think all of these are basically, so I know what pop count is. Let's just write all of them. So this is clear 0. I think this is seat. I don't know what that does. But I know what this one does. So this counts all of the ones in the binary representation of the int. Maybe, I mean, we don't actually need all of these or any of these, but I'm just gonna write them down next just to make sure we have them for now. And then maybe eventually we want to somehow check that we've matched all of them, but let's figure that out when we get there. So let's do the binary operations, because these are the interesting ones, right? So these are the ones we actually use. So there's add, there's a sub, there's mul, there is div, and here we need to have two divs. We have one div which is for unsigned and one for signed. I don't even know what that means, but this is the signedness of these, so I'm just gonna leave it in there. Yeah, we'll see. So what else do we have? We have the reminder function. So, and reminder is also signed and unsigned. Okay. So I guess this is, I don't know what that is really. Oh, it's probably, yeah, because when you're dividing, you need to know whether or not to treat the sign bit as such, I guess. We'll figure it out. So you can AND these together, you can OR them together, you can XOR them together, you can shift it to the left, you can shift it to the right. Is there a shift right? Yes, that's what I expected, one that treats it as a signed number. So this is what's called a logical shift, and this is an arithmetic shift. So this shifts in zeros in any case from the right, and this shift from the left when you shift to the right, and this respects the sign bit and only shifts in ones if it's a negative number and shifts in zeros if it's a positive number. And then we have rotation functions, so these rotate bits to the left or to the right. And we're not really going to use these, but I'm going to add them here in the case someone needs them at some point. Like so. Oh, one is L, one is R. Did I always start with the left ones? Yes, I did. So that's good enough for me. So, do we have more integer stuff? So we have ibin up, we figured those out. ite stop, was that equal to 0? Okay, so we can check if a number is equal to 0. And that's 1. Okay. Then we have relative operations, and those are kind of important. So we have I32 eq. Are two numbers equal to one another? Are they not equal? So this is NE. Are they less than or larger than? And here again, we need to respect whether or not they're signed or unsigned. And I start with the unsigned ones everywhere else, so I should do the same here. Then we do the same, but for greater than. And then we have greater than equal, less than equal, and greater than equal. So this is LE and greater than equal. And all of these come in signed and unsigned variants. And that is it for the relops. So we've gotten to this point. Now we do the extend, wrap, truncate, and this is floating point stuff. I'm not going to deal with that yet. I don't even know what these functions do. But I guess since we're here, we might as well figure them out as well. So there is an I32 extend 8 underscore s. So extend 8 signed. There's an extend 16 signed. And then there's one that extends, but that one is only defined for I64s. And because we're only doing I32s for now, I'm not going to do that one. Okay, but then we have an I32 wrap I64, like so. I'll capitalize that one. No, I'm going to leave it small. And we have trunk and trunk saturate. I have no clue how that works, so I'm not going to do those. But well, maybe we'll find out what those mean. And I think that's the set of instructions I want to do for now. Then there are a few more. So these are the numeric instructions. Where's all of them defined? Here we go. So these are this is the control instruction. These are the memory instructions, variable instructions. Where does it define all of them? Okay, so where's defined which groups of instructions there are? It's a number of different categories, that's right. But well, I guess we'll just keep going and figure it out. So these were the numeric ones. Let's do drop and select. And then we keep going. So the variable instructions are local get, and this accepts a local ID, local index, which, well, is just an int as well. All of these indices are ints, but they're U32, so you have to be a little careful to make sure they're always unsigned. Local set, local index, we can t, which is a set which leaves the thing you're setting on the stack, and then we have global sets and gets, and these use, I'm assuming, global indexes. Yes, so global index, and it's going to complain because I need to specify global indexes like so. All right, so these were the variable instructions. Next up are memory instructions, and memory instructions accept a memarg. So there's a memarg type, which is a record of offset, which is an int, and alignment, which is also an int. And we'll have to, it's a bit tricky because you have to default this in the textual syntax, so we'll see how this looks when we're encoding things. I'm not entirely sure yet. So maybe I'm just gonna give these groups names. So these were the memory instructions. No, these were the local variable instructions, that's what they're called. So variable instructions. These were called parametric instructions. And that's because they're really, they work on the stack parametrically, so it doesn't matter at all what type or things are on the stack. So that's what I call parametric instructions. So what's the next thing? The next thing are the memory instructions. And these are kind of important. So these are the instructions that work on Webassembly's linear memory. So well, not every, but if a module declares that it wants to use a memory in Webassembly, then it gets, at this point in time, 4 gigabytes of linear memory that is free to write and read into and from. And it's the Wasm engine's task to properly map that memory and provide it. And this is part of what makes the WebAssembly module safe sandbox for executing code. Well, if we leave out the part where nothing is safe on modern CPUs. Okay, so again, we're just going to do the i32 ones. So we're going to start out by saying there's an i32 load, which takes a memarg. And these memargs are optional. Let's see, memory is exactly load and store instructions for different value types. They all take memory immediate memarg that contains an address offset and the expected alignment, expressed as an exponent of a power of 2. Integer loads and stores can optionally specify a storage size that is smaller than the bit width of the respective value type. In the case of loads, the sign extension mode SX is then required to select appropriate behavior. Sure. We're just going to do loads and stores for now. And again, these exist for all the types. So floating point numbers, i64s, i32s. We're just going to do i32s for now. And then we have load 8. And when we load a value, we have to load it as a signed or an unsigned value, so that this one interprets the first of these. So the 8 says that we want to load a number that so we want to load into a i32. We want to put an i32 on the stack, but we want to load it from 8 bits. So this is only suitable for storing small numbers. But then we need to understand if the first of these 8 bits is a signed bit, or if that's paired. So if it's a signed number, then the first bit of that whole 8 bits is going to be the signed bit, and otherwise we're going to interpret all 8 of these bits as part of the actual number. And we're going to do the same for 16. And we're going to do, well, okay, so these, we can only store a 64-bit number in the space of a 32-bit, so this one is not provided for i32s, so that's good. Don't need to worry about that. And then we can ask for the memory size. So this asks the engine how much memory we've allocated so far, and we have an instruction here which grows it. Which grows the memory. All right, so now we get to control instructions. And I mean, we could have probably just copied this data type from the Haskell implementation, but I think it's good to just go through and read these things and look at what we have available and what we can use when we are going to generate some WebAssembly at some point. So there is a block type here, which is either a type index or a value type. And I don't know, well, it's defined as a sum here or as a variant, so we're just going to do that. But why is there a question mark up here? Is this value type? Okay, let's try that. Let's try to figure it out. A structured instruction can consume input and produce output in the operand stack according to its annotated block type. It is given either as a type index that refers to a suitable function type, or as an optional value type inline, which is a shorthand for the function type of this thing. Which I'm not sure. This seems like sugar to me. But maybe it's not, because it is possible that this ends up showing up in the bytecode. And so then we'll have to, when we run into our encoder, we'll have to be able to do both. So I'm gonna assume that we need to be able to do both. So a block type is either a type index, which is going to be a type index. We have a type for that, or it is going to be a block value type. And this is actually an optional thing. So this is a maybe, well, maybe we have a val type here. What do you not like about this one? Unable, oh yeah, it's just that we're not. Okay, so control instructions have, the first one is the NOP, which is an instruction that does nothing. NOP stands for no operation. Then there's unreachable, which is a trap. Hey Vince, how's it going? Nice to have you. How's it going? I heard you basically got your lockdown decided on the night of Halloween. How did that go? Did all the people stop partying and go back home? So yeah, I'm assuming I knew you would be enjoying it, that's for sure. Okay, so now for a block, we have a block type, and we have an array of instructions. So these are the instructions inside this block, and then it ends with, well, an end. But we're not going to write this down here. This is more for when you want to write a parser for it, I'm assuming. I don't think there's any information, like you can't write a block that does not end. So we're not gonna add it to our abstract syntax here. Okay, so what is a loop? A loop also has a block type and an array of instructions. If has a block type, a list of instructions. This is the thing that produces the condition. Then it has an else, and this is the. Oh wait, no. It assumes the condition is on the stack when it happens. Parting Frog was never listening to Crazy Frog song. Oh, that sounds fun. Yeah, Crazy Frog is exactly what we need. Oh no, and more follows. Yeah, the great animation of the running zombie. Well, I think it's actually kind of cute. So yeah, I'm assuming the whole lockdown part didn't go all that well at Halloween. Might have been a good idea to think of that a day before. Okay, so we can break using a label index, and we don't have these yet. So let's do that. So we can break with a label index. We can break out of an if, I'm assuming, with a label index, and we can break, and this is table stuff. This is really useful if you want to implement efficient pattern matching, but I'm well, not going to go too deep into that. But okay, so what does a table break have? A vector of label indices and a label index. Here you go. This is essentially a mapping. We have return. We have call. So return is a scoping operation. Basically, it or like it respects the block scope here, and it knows to return to the outermost of those, I think, or something. Or like it's like a really quick way to break out of all the surrounding blocks, I think. But I'm not tell you. So now, oh, this is interesting. Okay, so now things are getting interesting. So we can call a function index, or we can call indirect. And when we do an indirect call, we actually have to specify a type index for the type of the indirect function call. And that's going to be very interesting when we get to actually implementing a small functional language. Are you making a custom backend, or is this primarily an FFI? So this is, okay, so it's neither of those. I'm not making a PureScript backend. This is a library for generating Wasm from, so using PureScript to generate Wasm, but not because I want to compile the PureScript language to Wasm. I want to compile a smaller lambda calculus-ish language to Wasm for teaching purposes. But I'd like to do it using PureScript. The generating of Wasm part, because I don't get to write PureScript a whole lot anymore, and I think it should be kind of fun. So that's what this is. What we're doing here is we're defining the abstract syntax of WebAssembly as a PureScript data type. And so, well, according to this thing, we should be done. We don't care about any of the semantics of this. So this specifies the semantics of this. Or like the execution bit, but this kind of specifies what this syntax means. We don't care about any of that, at least not yet. Right now, we just want to define it and be able to encode it, and then maybe we'll think about what these things mean when we get to using them. All right, so I'm going to assume that this is good enough for now. We can extend it to match all the other stuff. Maybe we can just have it to do here. Add instructions for non-I32, 32s, as well as, and we did not specify all of the CVT ops, so I don't even know what that means. So that's basically this block. We basically completely skipped this one. Okay, so got all the instructions, and we're backtracking again. So we were here. This was what we're defining. We were defining what a func is, so that we could finish the function section of WebAssembly modules. So the next section is tables, which I'm going to skip for now because we're not using tables yet. But we will eventually. I'm just going to add them. We might as well. So a table is a vector of tables, so an array of table. Okay, so what's a table? A table is a table type. Okay, so what is a table type? Wait, let me see. Does type mean anything? Is type defined as anything? No. Table types classify tables or elements of element types within a size range. Okay, so what are we doing again? We're saying that this is a record. What does this mean? Why is there a bracket around this? Or are we just naming the thing? I don't know. I'm gonna make it. Yeah, let's just do it like the spec did it. So a table is equal to a record with a single element, and that element is going to be called type, and it's going to have a table type, and a table type is a limits element type. So limits classify the size range of resizable storage associated with memory types and table types. If no maximum is given, the respective storage can grow to any size. So this is well, we'll figure it out, I guess. I'm gonna call this type. Okay, so let's call it limits for now, but I have a feeling that we might want to call it table limits or something at some point. And so limits is going to be a minimum value, which is an int, and a maximum value, which is an optional. No, wait, it's not. Is it optional? Yes, that's a question mark, right? So yeah, so this is a maybe int. Okay. Table types classify tables over elements of element types within a size range. So we have limits, and then we have an element type here, and an element type is a func ref. What is a func ref? How is a func ref defined? The element type func ref is the infinite unit or union of all function types. A table of that type thus contains references to functions of heterogeneous types. In future versions of WebAssembly, additional element types may be introduced. Okay, so that's why that's specified like that. Okay, so a table type is a thing which has a limit, or limits, which is limits. Yeah, thanks for that hint. That's why the syntax error was there. Good. And then it contains a element type. And that's an element type. And element type for now is just funcref. Damn it, I can't type. It's just funcref. Okay. All right, cool. We can have a bunch of tables apparently per module. All right, that's tables. Next up is mems, and mems is the memories. So mems is an array of memory. So let's look at what a memory is defined as. Well, it calls it mems. I'm gonna use memories because I don't like all this unnecessary shortening of things. So a memory is apparently a single element record with a type field. Got a few of those, and then it has a memory type, and a memory type is just limits. So I'm not going to bother creating a type for that. I'm just going to call that limits. Maybe not. Let's just do that. Okay, so memory type is just limits. Okay, so we go back. The min size and the limits of the memory type specifies the initial size of the memory, while its max if present restricts the size which can grow later. Both are units of page size. Memories can be initialized to data segments. Memories are through memory indices, starting with their smallest index, not referencing a memory import. Most constructs implicitly reference memory index 0. Okay, so well, if we already know, I can just type out that there is going to be a memory index. All right, so that's mems. Now let's do globals. So globals is an array of almost all of these are vectors, as you can tell, of global. And global is okay, so an array of globals. What is a global? Well, a global is a record type with a type field, which is a global type, and a init, which is an expression. We just called expr? I hope so. What is a global type? Let's figure it out. A global type is a value type that is mutable or immutable. So we have a record here, which contains the, I'm just going to call it mut, and that's the mutability. Well, let's call it mutability, come on. Like so, and the actual type, which is a value type, or val type, apparently. Okay, and then mutability is either const or var. I can type mutability, like so. All right, so that's global types. Let's go back. We did globals. Now we get to elms. So elm is a vector again of elms. So what is an elm? Stay tuned to find out. So an element segment. The initial contents of a table is uninitialized. The elem component of a module defines a vector of element segments that initialize a subrange of a table at a given offset from a static vector of elements. Okay. So this is what initializes these tables and memories fields. So we start out by saying, give me a table index. So this is a table index. Do we not have those yet? Okay, let's write them out. So we need a table index. I'm assuming that's just an int. Yeah, they're all. Okay. Then we have an offset, which is actually an expression. So that's tricky. Okay. Then we have an init, which I'm assuming is a bunch of functions that initialize or something. Yeah, so that's an array of func indexes that I'm assuming are going to be called to initialize that memory. And the offset is given by a constant expression, which means something, but we can't. That's something for the type checker, but we're not writing a type checker here, so we don't care about that bit. Means math. Const. Oh, you mean because there's because there's semantics here. Yeah, these are just some. Okay, yeah. So these are. This is. Yeah, I think this is the typing rules. Yeah, this is the typing rules. So this is a specification of how to type check these things, but we're not doing that, so we're fine. Also, WebAssembly is not actually hard to type check, so we would be able to implement that, but it doesn't contribute to us being able to compile something to WebAssembly. It would be interesting if we were writing a WebAssembly interpreter, but we're not doing that, not yet anyway. If we ever want to, we can figure that one out by then. Okay, so modules, we're all the way down to data. So we did elem. Let's do data next, which is another keyword, but that's fine. And this is a vector, so an array of data. I'm just going to complain. So what is data? Data is a memory index. Luckily, I already defined that. A memory index. And then, so this is the memory we want to initialize some data in. And we want to offset it at some expression. So this is the offset. And I'm assuming that's a constant expression again. And we're going to initiate this with initialize it with a vector of bytes. And bytes are just ints, but I'm going to say byte equals int here because, well, they're not really. We need to be careful, right? These should only be 8 bits wide, but yeah. This is JavaScript, so we don't have things like that. We just have numbers. Okay, so what is start? Well, for one, start is optional. So this is a maybe. And then what is start? Well, start is a function index, and I'm not going to bother writing down start there. I'm just going to type func index right here because that's what it is really. So this is this makes it so that when we call wasm time or something on our wasm file, it knows which function to call as the main function. It's not like there's a convention for just having a function called main that starts the thing. You can specify which function starts it. Now we have imports and exports. So imports is an array of import. Okay, so what is an import? An import has these things. It has a module, which is a name, which I'm assuming that's just a string. Yeah, that's just a string. Well, it's really a UTF-8 string, so we need to be careful when encoding that because JavaScript has UTF-16 strings, but I have a feeling we can figure that one out. So an import has a module, which is name. It has a name, which is a name. And let's just do that for documentation purposes. And a description, which is an import description, or just desc. And an import desc is a sum type. Okay, so that's data. So an import desc is either a func, and I'm assuming we're going to do func import here. So, or no, let's write this first. So import func, and import func carries with it a type index. And now we've got identity following us. Identity.js. Hey, how's it going? Oh, you're from the Discord, right? How's it going? Wait, aren't you the guy that does all the crazy address stuff? So this is, yeah, and I knew. Oh God. Well, okay, so we're doing WebAssembly. That's good. That's good. You're about to stream. Well, that's cool. I probably won't be streaming for too much longer. I've been going at this for more than over an hour by now, I think. I just want to finish defining the abstract syntax for WebAssembly in PureScript. And once we're done with that, I might just see if I can figure out how to raid your stream then, I guess. I don't know how that works yet, but I think Streamlabs somehow lets me do that. But we'll figure it out when that time comes. You enjoy your stream though. Okay. But we are going to continue defining what imports in WebAssembly are defined as. So we can import a table, and that carries with it a table type. Have we defined what a table type is yet? I think we might have done that actually. We have. So there we go. Our hard labor starting to pay off. Damn it. And table types. So what else can we import? We can import memories. It's not an import, not a Discord. Sorry, I meant Discord. There's a streamer Discord or something, which I don't know if Vlad initiated that, but there's a couple of people streaming functional languages in there, and it's been kind of a nice community, kind of motivated me to stream again, thinking of the old live stream page times when there was like a little community of streamers. All right, so we need a memory type. Do we have that? Yes, we do. And we can import a global, and that's a global type. Here we go. Here we go. That looks good. Then it says each import is labeled by a 2-level namespace consisting of a module name and name for an entity. Yeah, we've done that like so. Cool. All right. And the last field a WebAssembly module has is its exports, which is an array of export. And an export in WebAssembly is defined very similar to an import. Just that there's no module here, so just a name. And then the desk is an export desk though. So let's define what an export desk is. And I can tell that it's some type from looking at this. So it's an export desk. And we can export functions, which is going to be a func index. Or we export a table, which carries with it a table index. Or we export a memory. Export memory, which carries with it a memory index, or we export a global, which is carrying a global index. And then just doing a bit of formatting here. All right, and I think that should be the abstract syntax. Oh, we need to go back a little further. No. Structure modules. Here we go. Yes, this, as far as I can tell, it has been the abstract syntax of WebAssembly defined as a PureScript data type. And so the next task really is to take all of these types and to define binary encoders for them using the functionality we've built in the encoder before. And then we can define WebAssembly programs as instances of these PureScript data types, encode them to binary, and try and run them with Wasm time or a browser. So I hope this was instructive or fun. I'm gonna leave it at that. And try to rate identity GS. Okay, so let's try and figure this one out. What do we have? Oh no. Messing things up here. widgets. I don't want to end the stream. There's a dashboard here. Streamlabs Dashboard. Maybe we can use this. No, that does not look like what I'm looking for. I think I saw this somewhere. That was like stream actions or something. Mini feed. I think it was called stream actions or something. Studio mode. Help. Nope. Well, this is just some kind of seam editor. Huh. All right, let's try to do it from within Twitch then. So I want to go into the create a dashboard, I believe. So stream manager. Yeah, that's where it is. So raid channel. We're gonna raid identity GS or something. Okay, I have to figure out the name first, apparently. So, is it just identity.js? Like so? Maybe he's not online yet. Let's check his Twitch real quick. Yeah, that's the name. Oh, he's not online just yet. Okay, so I can't raid. You're just gonna have to go over there. I'm just gonna give you the link, I guess. So, if you want to keep watching some programming, and if you'd like to see some mind-blowing stuff, how do I turn off the stream editor? I want to see this. Damn it. Yeah, Twitch is too hard for me. Or if you want something easier, Vint is going to stream it a bit. That's also going to be fun. All right, cool. I'm out of here. Have a good one, everyone.